This is part one of our lecture video series for Wednesday, May 10th, where we are going to look at a phase change diagram and kind of look at the relationship between energy and how that affects how a substance will change its phase. So let's remind ourselves of the different phase changes that a substance can undergo and the associated enthalpies or heats of those phase changes as being either endo or exothermic. So remember endothermic, endo, interior. This is something that requires energy. So energy is absorbed in order for that phase change to happen. So energy absorbed. And in this class, we often are talking about thermal energy, so heat is absorbed. Compared to exothermic, exo, outward, exoskeleton. This releases, REL is a shorthand of releases, so releases energy. So we can say again, energy is expelled. Or heat is expelled or heat is released. So of our endothermic phase changes or phase changes that require energy in order to occur, we have the phase change of melting, otherwise known as fusion. Again, this is where we go from a solid into a liquid. And we have an enthalpy of fusion, delta H fusion, or heat of fusion, and that's the amount of energy required just to go from solid to liquid. Okay, melting, solid, liquid. So that is our first endothermic phase change. All right, that brings us from solid to liquid. Now we have liquid to gas. So we have the process of boiling, or what we call vaporization. Which has a heat of vaporization associated with it. So this is the process of going from some kind of liquid phase to gas phase. And then we also have one of my favorite phase changes, sublimation. And this is where we go straight from being some kind of solid into being some kind of gas. So all of these are phase changes that require energy: fusion, vaporization, and sublimation, meaning that all of the signs of these enthalpies are going to be positive. So I've got the positive heat or enthalpy of sublimation. So those are the phase changes that require energy. Let's now look at the phase changes that release energy. So these are phase changes that have a substance go from a high energy phase to a low energy phase. So let's start with our highest energy phase, which is our gaseous phase. So if we're going from a gas to a liquid, we call this condensation. And because this is a stabilizing process, meaning our substance is ejecting or transferring any energy out of its system itself, it is going to be exothermic. So that's what I mean when I say stabilizing. You're getting rid of you're getting rid of excess. I don't want to call it excess, but you're getting rid of energy inside you. So you can imagine, like, if you were to somehow be able to transfer energy out of yourself, like, I don't know, from walking to sitting down, right? Transferring energy out of yourself, you'd become more stable. So condensation, again, this is the exact inverse of vaporization. So this is where we go from a gas to a liquid. Okay, let's look at our next exothermic. So our next highest energy phase to low energy phase transition. So we've done gas to liquid. That means we've got up next liquid to gas. Sorry, not liquid to gas, liquid to solid. So we call liquid to solid the process of freezing. And again, this is an exothermic process. So the associated energy that is released upon changing phase from liquid to solid is going to be negative. Okay, so this will take us from our liquid and take us to the solid phase. And then finally, we can go straight from our highest energy phase, the gaseous phase, down to our lowest energy phase, the solid phase. This is called deposition. Thin layer deposition is actually like an engineering and chemical process that's really commonly used in the development of microchips, right? This is when you want to take a gaseous substance and use kind of the inherent homogeneity of that gaseous substance to adhere it to some solid surface, so cause it to become a solid. So deposition, again, this is exothermic, and this is where we go straight from our gas phase to our solid phase. Okay, so why is it that we're doing this review? Like, why are we just kind of reviewing the last lecture from last week? Let's look at a phase change diagram. So let's define what's happening in a phase change diagram. So a phase change diagram shows how the addition or removal of energy, typically heat, Q, from a substance causes some kind of phase change. And specifically, it shows us the temperature at which each phase change begins. So what do I mean when I say each phase change begins? So if I were to look at, I don't know, let's say the process of freezing water. So if I had a sample of water, that was liquid, and I removed heat from this in order to slow those water molecules down. At the very first moment where ice is being formed, so like the very first moment where even in my liquid sample, I've got perhaps like one crystalline structure of ice that's formed, despite my entire substance not being fully solid yet, because I've begun to form my solid, this is going to be the heat or the temperature, that's associated with the sufficient amount of heat transferred out to cause our freezing. All right, let's keep this going. So let's say that we were to keep pumping heat out of our system. So we were going to cool this liquid water down continually. So we're going to remove even more heat from our system. By the time we now have fully solidified all of our water into ice, this is the kind of, how would I say this? This is the last or final amount of heat required or released to freeze all of our water. And the thing about these temperatures, right? These temperatures that are associated with heat transfer out of our system is this is what we call the freezing point. So right at the temperature at which we begin to see the formation of ice, that is our freezing point. And if we keep our substance at that temperature, right, we've pumped then enough amount of heat out of the system that we have completely gone to solid, and then we will be dipping below the freezing point after that. So this isn't kind of like a conceptual, like literal diagram sketch mock-up of what we see in a phase diagram. So let's look at a phase diagram. All right, so we've got a couple of things going on here. So it's a phase change diagram, excuse me, it should be more specific here because phase diagrams are different. So example, phase change diagram. So this is just a general one. So here on our y-axis, we've got a temperature axis. And on the x-axis, this is the amount of heat. So we have increasing heat Q and increasing temperature T on our x and y axes respectively. So let's see here. In region A, so I'm looking at, in region A set of temperatures and amounts of heat that will keep my phase in the solid phase. So that's what this little kind of array of particles is here. This is showing the solid phase of matter, meaning that at any range of temperatures and heats found within our system that are found along this kind of curve right here, we're going to be found in the solid phase. Now then, what happens if we were to keep increasing the amount of thermal energy and thus upping the temperature of our system to the point where we first see signs of our solid beginning to melt? So this is region B on the phase diagram. Where exactly at this temperature here, and I guess here, let me move this dashed line a little bit because it should be a little lower. So exactly at this temperature here, if I could draw a straight line, don't know that I could, save my life. All right, once we've hit this point, this is where we have now hit a sufficient amount of energy that has been increased or put into the system such that a phase change occurs. So if we are in fact looking at increasing, so let's work our way up this curve, then we are going to look at the process of going from solid to our next phase to liquid. So this is our fusion. And this temperature at which we first begin to see signs of a phase change, this is our freezing point. You could also think of it as our fusion point, because if we were to go back down the curve, we would see freezing. All right, so what does that mean? Like, why is it that I see this kind of line extending here? Like, why is it that it's not just like a single point, right? Isn't my freezing temperature just a single temperature? And the answer is because, remember, this freezing point is the point at which we first see a phase change happening. So we have this duration of heat input that is going to allow us to have this kind of mix of two different phases that exist until we finally have reached the point where we can then up ourselves into the next highest energy phase. So what we've got here is we've got kind of like a phase equilibrium going on, or a mix of solid and liquid. So in region B, we have both solid and liquid. So notice this is at one temperature, the freezing point. However, we have to keep putting energy into the system in order to get all of that stuff to fully melt. Okay. Now what? How about we look at what's going on after the point at which we've put enough energy into our system to finally free or unfreeze or fuse or melt all of our solid. So at this point, we are now in kind of a less organized, higher energy phase, the liquid phase. Our molecules have a little bit more kinetic energy due to there being more thermal energy that is in our system. So this is our liquid phase. And so what this part of the diagram is saying is that any temperature range from here upward, and then any heat energy here, like this, is going to result in us being in the liquid phase. So like over here on the left, right, here's a series of temperature and heats that result in us being in the solid phase. Here is a series of temperature and heats that result in us being just in the liquid phase. All right. Well, what happens when we hit just exactly the temperature needed or the amount of heat that is needed in order to not perfectly, but begin to not freeze, stuck and frozen, to begin to vaporize our substance. So go from a liquid to a gas or undergo a phase change. So we're looking at this exact point here. Okay, this temperature is going to help us go from a liquid to a gas. We call this the boiling point. And at the boiling point, we will see both of our phases, liquid and gas, exist because right at the boiling point is when we first see signs of liquid going to gas. So we see things like the process of vaporization, and then we also see things like the process of moving in the opposite direction, condensation. All right. So that means that in region D, we are at our boiling point, and we see both gas, condensation, or vapor. Okay, we see both vapor and liquid. And let me do this in order. Let's go low to high. So liquid and vapor are present. Where again, B, this is at the freezing point, and D is at our boiling point. This is so horrifically not a straight line. I'm so sorry. Okay, is this any better? It looks a little better. Okay. So now we have reached our boiling point. So this is the point where we first see formation of gas. And we're going to continue at that temperature where our substance is absorbing more and more and more heat until we have finally put sufficient heat into our system to boil every last molecule of that liquid. And we can now fully exist into our final phase, which is our high energy phase, our gas phase. So we've got these high amounts of thermal energy, right? A lot of heat in this system. So we've got a lot of kinetic energy. This is why we call our gas phase to be our highest energy phase. So this is a gas. And if I were to look along this curve here, then I would see that at any amount of heat pumped into this system, that ranges from here to here, and any temperature that ranges from here to here, this is what would keep us in our gas phase. So this is our series of temperature and heat that would keep us in the gas phase. So once we are at point E, we are fully in the gas phase. Okay, so the important parts of this diagram, like really what you need to understand about what's going on here, is that the freezing points, the melting points, the boiling points, etc., these are all temperatures that are the temperature at which there is just enough heat to start the first molecule changing phase. And we're going to continue to absorb some amount of heat until we have fully changed phase of all of our substance. So that's why we see these flat line regions here, shown in purple and in orange. So this is a phase diagram. Phase change diagram. All right. Now that we've talked about phase change diagrams, let's look into phase diagrams, which are a little bit different because phase change diagrams relate temperature and heat and show us things like our boiling point, our melting point, our freezing point, yada, yada, yada. And phase diagrams are a little bit different in that they don't relate temperature and heat, but rather they look at a different series of physical or lab conditions like pressure and temperature that will result in a substance existing at one phase or another. So let's get into phase diagrams in part 2 of this video coming up next.